All right. So I'm going to go ahead and go to a new statistical test, Welch's tests. And so, oh, sorry, Welch's t-test, technically. So I'm just kind of refreshing the page. So Welch's t-test is like, wait a second, we've already done a t-test. What is this Welch guy doing here, right? Well, basically, as we saw, talk about when a student's t-test, we basically have that from, oh shoot, I forget his name now. See, that's what happens when you don't put your name in the book. So student's t-test, the guy who worked for Guinness Brewing Company, he's the one who developed student's t-test. I can't remember his name. Anyway, fun history. But if basically a student t-test when it's not the right kind of test to go through. So a good place to go, honestly, if you're like, what is this exactly? Like, I can't remember exactly. Wikipedia is actually a really good resource for these kind of things for statistics. But basically, a student t-test, we assume certain things. For example, the sample size and the variation are the same between two samples, okay? And if that would be true if we're looking at, for example, a population and we're taking the samples from the population, but sometimes our samples might actually be different, like maybe just by the fact of what we have. So if we don't have that, our t-test can actually not do very well on performing our test because it's basically assuming this nice even variation in sample size. So enter Welch, right? So Welch basically says, all right, we're going to do a variation of t-test, but this time we're going to adjust for that difference in the t-statistic. So one thing I want to emphasize, because this confused me for the longest time, a statistic is something that's grabbed from like that sample, right? When we have a statistic, it's something that we kind of measure, right? So you'll hear me say t-statistic and t-value. Those are the same thing. So just kind of know, like when you hear that t-value, t-statistic, that's the same thing. We're basically pulling it from our sample, okay? So again, really complicated equation. Don't stress out about it. It's not that bad. Also, you probably don't have to ever really remember it. The curriculum actually shows this directly because there's not a built-in part, at least for Python. But anyway, here's the equation. So it's actually not as bad as it looks. Like you're like, oh my gosh, there's so many variables in this. But essentially what's happening here is you have two samples, x1, well, you can say like the mean of x1 and then the mean of x2. Okay, that's what the x bar is. And then this S1 and S2 are representing the sample standard deviation. So the variance of that sample, okay? And then this N1 and N2 are just representing how many are in the sample. So in a t-test, we assume that the sample, the variance, right? Sorry, the sample variance and the sample size are the same. But in this case, our t-statistic is actually derived from actually keeping these in account or accounting for those two parts. The sample standard deviation and the sample size. So by including these parts, we actually can pull this out now and actually say, oh, we incorporate this in, and we get a new t-statistic. Now there's another part in this is basically, it's like, well, one thing we talked about in the t-test is we had degrees of freedom. And actually, I think Ali was the one who asked me this in a one-on-one, said, what is the degrees of freedom? And I said, that's complicated. Basically, it's just how many ways you can vary. And usually for a student's t-test, we just say 1 minus the number of samples. Simple, 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 right? Well, guess what? Welch isn't simple, right? So V is our degrees of freedom. And basically, again, don't think like, oh my gosh, how am I ever going to pull this together? Basically, all you have to know is that this V1 and V2 are the number of sample, like the degrees of freedom for each sample. Basically, N1 minus 1, okay? And it basically has these parts in there. And it's accounting for saying, okay, here's your original degrees of freedom. But since the sample sizes are different sizes and our sample variation are different, we account those two together and form a new super degrees of freedom. And that's essentially what's going on here with this V. So again, what is going on exactly in this case? I wouldn't stress out too much about it. It's like, what is going on here? Basically, it's saying that we have different ways we can pull this information from. And since our sample sizes are different sizes, we actually need to take that into account. So this is where this degrees of freedom comes through, okay? So again, basically, I'll try to cross this out. It's not a scary one. It's just a misunderstood, right, equation. So you have this really big equation. Most time you won't want to calculate this yourself. You can. I think the curriculum actually shows what this would do. But once you have that t-statistic, right, we can actually compare it with your critical t-value. So the way I kind of imagine this, like I have a little note here, battle it with, it's like your t-statistic is fighting against like your critical value. So your critical value basically is like, all right, this is what I need to have in order for how much weirdness am I allowed to accept? And our t-statistic is like, this is how weird my sample is. And you say, okay, how weird is my sample versus how weird is am I willing to accept? And that's what our t-statistic is. Or what would be our p-value, our p-value versus our alpha value. Okay, and also note, I put a little here, is t star. Well, I didn't talk about this last time, but sometimes you'll see in some literature say t star. That t star represents your critical t value, which I know everyone uses their own different notations, probably because statistics is used in every field in science. So that's probably why everyone has their own like special way of notating it. But just know that t critical value is the same thing as a t star, if you ever come across it. And one way we could also do this, instead of comparing our t critical value and our t-statistic, is that we can use the degrees of freedom to convert this into an alpha critical value and a p-value. Okay, and that's really what we're doing. And usually when you look up a t critical value, usually that's what you're essentially doing. You're taking an alpha value and inputting it into, say, all right, I want this alpha value, convert this into a t critical value for these degrees of freedoms, and that gives you a value. You can also go the other way. So computers, again, are really nice because they can compute things for you, and they can actually say, okay, I'm going to take this t critical value, and compute the alpha value itself. Okay, but the main thing here is just know that the Welch's test basically takes into account that when the samples are not the same size and or the variation is different between the two samples, and you get this whole part. Okay. Any questions on like again, I guess not so much the equation, but like why we would do this? Okay. Thumbs up, thumbs down for understanding. Sideways. See some sideways. Don't look at the equations too hard. It looks more intimidating than it needs to be. You will probably not really see this ever unless you go deep into like how to calculate this, because we have coding, right? So one thing is the curriculum shows stats models, which to be perfectly honest is a better stats package than SciPy. But I wanted to show you what SciPy would look like, just so you have this part. Stats models OLS is probably better standard. To be honest, not enough people probably use it. Probably because all the statisticians are hanging out in our land. It's a different programming language. So just know we kind of like, as Python, we're kind of like the stepchild of like statistics. You're like, oh, statisticians like adopted Python, and I guess we could use this. So we don't have as many like nice cool tools as R, but that's okay. Okay. So one thing I'm going to show is SciPy. Note that it has a built-in t-test. It actually uses Welch's test like subtly. Basically, it says, all right, when the equal variance is false, okay, it will use a Welch's test by definition. And it even says in here in the documentation, which I linked over here, is that Welch's test equal variance. It says, oh, false, perform a Welch's test. So it just does that. It's just that it calls it variance is false. So that's why it's built into here on the SciPy stats model. Okay, so I just built a little function here to compare two different samples. Oops. Our two different samples here. And basically all I'm doing is saying, all right, stats.t-test index, right? Basically I'm performing a two-sample t-test. I'm sorry, not two-sample, two-sided. Ooh. Mistakes. All right, two-sided t-test, right? And we have alpha, or A and B, right, are two different sizes, or two different samples. And we basically say, okay, let's do a student's test and a t-test, or a student's t-test and a Welch's t-test, okay? And so all I'm basically doing is that what this returns is essentially either a t-value, or it returns a tuple of a t-value and the p-value. So we'll see what this looks like for equal variance. I just basically cooked some data. You can see here basically the same mean, same variance, right? And our same size, okay? So these are basically equal variance, equal size. And we can see here is that I basically had to calculate my student's t-tests and my Welch's t-tests, and our t-statistic is basically the same because we should be getting the same thing because there isn't a variation in size or anything like that. So a t-test should be perfectly fine, okay? And you can see the difference between the two t-tests. So the first value is actually our t-statistic, and our second value, right, in that tuple is actually our p-value. So it converts that p-value into nice, beautiful, nice, easy p-value that we're all familiar with. You don't have to worry about no stinking t-critical value, right? So it's kind of nice and convenient, right? Now, if we have equal variances, but the sample size is different, right? So you can see here, the first one is size of 50 different parameters, or 50 different individuals versus 500, right? So this is clearly a different sample size, right? Still pretty decent. The 50 people is not too bad for most statistical tests. And we actually compare this now, we see that our students, our t-statistic on here versus our Welch's, it's like, oh, that's a little different. You can see that very difference right here. And you see this difference is that our Welch's basically is about 0.03 smaller for our t-statistic. Now, this should mean absolutely nothing to you because it depends on our critical value. So we can actually use the p-value that's built into this thing. And you can see here our p-value is about 0.0297 versus 0.0287. So you can see here our p-value is off by about 0.00 or 0.01 almost, right? So you can see it's a little off. And if we get this very extreme, like this is a little more extreme than needs to be. But if they have a very high value, I actually don't know how much that would be different. You can see we get higher and higher. So this is where like our t-test is starting to diverge on how well it would perform. And then if we got really extreme, we could change, like, for example, the variation and such. Okay, so cool. Any questions on that? Sound good? Okay, thumbs up if that makes sense of like why we would use Welch's tests. Thumbs down, you're like, I don't know what the difference is. Okay, I see some sideways, some thumbs down. So thumbs down. So Giovanna, do you have a specific question on this, or like what's tripping you up?
I'm not really getting what's the difference between students and Welch. What is changing there?
So the biggest change, and this is where I'm kind of hiding away a lot of the magic that's going on here, is really coming down to the fact of how they consider degrees of freedom and how they consider the t-statistic. So basically what's happening here is it's being like the t-test was, if you remember this, is the difference between the two means divided by the standard deviation or the sample deviation. And so this right here basically is saying, well, those sample deviations are not the same thing, so we have to take those into account. So basically, if I were to like redo this calculation down here, okay, what would happen is that these would be different. So if they are the same, in fact, like, so for example, N1 equals N2 and S1 equals S2, this basically would be 2 times, 2s squared, which would be 4 plus 4 divided by those two parts divided by 2. So that part would actually cancel out, and you actually would get just the square root of s squared, which would just be s. So basically this part would turn into just s. But because if they're different, if there's a different size or if there's a different S1 size, S1's variance, right? Then you would start getting a little different for your t-statistic. And basically it's like, why does this work this way? To basically wave my hand over it is because of math. Basically is that Welch just said, hey, this is another way we can determine, are these things actually different? And this is where like, you're like, but how did they come up with this? This is where it gets really complicated, but we could dig really deep into math and say, okay, this is a different distribution in realistic parts. And this is where, like, I always say, like, statistics feels very like, this is the number and just go with it, because it's not super clear exactly like, well, what's a good t-value? And this is where really it comes down to the fact that it's built on the fact of like using something like Bootstrap and showing this parts. And basically it comes down to the fact that it just works better. If that's unsatisfactory, I'm with you. But basically the one thing you should like really think about Welch's test is that it's considering when the variation is different between the two samples and or the sample size is different in each value. And that's why we see on that bottom one, when I put a very different sample size, you see the difference between our t values and then ultimately the p values itself, which is what determines, like, so this like one right here, if I had like 0.0, our p value is like 0.049 and then 0.051, that could make or break it saying whether something is critical or not. So this is why there's that difference between the two. Does that help clear things up a little bit, Giovanna? Okay, yeah, it's not super clear. And this is kind of leads us to, I'm kind of going over time. So I think I will keep this, for example, ANOVA and warnings for next time, and we'll bleed into the next section. But this is where, like, for example, ANOVA is another test we can do that's specific. It's basically an extended t-test. It's a t-test for like multiple categories. In our, what's it called? Our Welch's test is another test. Welch's test is not the only kind of t-test you can do. It's very powerful as well as t-test. So those are the most commonly one used. But if you're like a ultimate like statistician kind of deal, there would be so many different hypothesis tests that you could do. And depending on situations, you might use those kind of things. And to be quite honest, to get to that level, it might take like a level of like masters going at it. But what's good is that you usually don't need to have those high level of different tests to do a good job. And this is where like really our t-tests and our Welch's t-tests are pretty satisfactory in the fact that like about like 99.99% of the time, you care about, like those are the tests we actually use. And then honestly, in data science, if they don't perform well, you do data generation. You basically perform your own tests within it and do other models. That's kind of the power of like being able to use a lot of data science and machine learning. Okay. Any last questions? I know I'm kind of over time, but anything else you guys want to ask before I close it up? Cool. All right. And again, this is on the GitHub repo. Phyllis, I saw you came in. I'll make sure to share this to you guys out. So I'm going to stop recording if you guys are cool.